So we just learned how to build a logistic regression classifier to our credit data set. And now I want to talk about another means of training a classification model. Decision trees, I think decision trees are intuitive, and the way in the way that they actually classify examples, and it sort of mimics a more structured decision process, and that's essentially what a decision tree is. It's that you're going to learn this tree. This tree over here on the right is a tree that was learned on our credit data set using different fields. And it's a literal tree that you input an example into, and it's going to sort of clink around until we get to the bottom where we're going to make a prediction. And so let's break down and try to see how we can read this tree. So in a decision tree classification model, we're going to learn a tree. And essentially, how do you read the tree is that you start from the root node. First, you're given some input as an example as input. And you look at the example and all of its features, and you look at the root node, and you see that there's a conditional statement in that root node. What you're going to do is you're going to check and see, like, okay, what does the statement say? It's going to say if the checking status no checking field for this example is less than or equal to 0.5. Well, it can only be 0 or 1, if you remember this field. And if it's true, we're going to go to the left. If it's false, and let's just say it's 1, it's not less than or equal to 0.5, we're going to go to the right. Let's just say it was true. Well, we're going to go over here. And then it says if the other party's guarantor field is less than or equal to 0.5, go to the left. If it's greater than that, then go to the right. Well, it's another field that's either 0 or 1. And so let's just say this is false. Let's just say it's 1. So we're going to go to the right. And then it's going to check the employment field for making sure that it's between 4 and 7. If that's true, we're going to go to the left. And let's just say that it's true. If it was false, we go to the right, but let's just say it's true. Well, if it's true, we're going to go to the left. And then we're going to get down here to what we call the leaf node. And the leaf nodes is where the decisions are made. And right here you can see that in this bucket, there are 22 examples in our data set that meet this criteria, where they have this checking status no checking field is less than or equal to 0.5, other party's guarantor is greater than 0.5, the employment 4 to 7 is less than or equal to 0.5, and they're right here. So there's 22 examples in our data set that meet that criteria, and 5 of them have the value 0, and 17 of them have the value 1, where you remember 1 is good credit risk and 5 is bad credit risk. So of all the 22 examples that meet this criteria, 5 of them are bad credit risk and 17 of them are good credit risk. And because majority of them in this bucket have good credit risk, we're going to classify our hypothetical example as class 1 or having good credit risk. And that's an example of how we can input and learn the tree, right? Input an example and then follow, break that example down and then follow it all the way down to a leaf node to make a decision. And so here's the thing. So how do you learn this tree? So from a high level overview, what's going to happen is the model is going to start, right, with 0 nodes. So we're going to start with 0 nodes, and it's going to try to figure out what should this root node be. And this root node is going to be a feature. It's going to be a split or a segment of a feature. It's going to find the feature that best segments the data. And the feature that best segments the data is one that has the highest imbalance. And so here we learned that of all the features we had for the root node, the checking status field, no checking less than or equal to 0.5, was the best field, even though it splits the data in half. The other half right here have class 0, the other half have class 1. And for a node to be like this, to where of all the examples that meet this criteria at this point in the tree, half are one class and the other half are the other class, that's called an impure node, which is not horrible. It's quite common. Most nodes are impure, but it's way too balanced, and we don't really like that. We like to be able to get something that really has an imbalance between classes, because that's going to make a decision a lot better. For example, if you look down these leaf nodes here, this leaf node right here that I have my cursor on, 40 of these, 40 out of the 44 are class 1 and 4 are class 0. And that's good because that says that if you're in this class, chances are you're class 1. But if the answer was like 22 and 22, right, the values were 22 and 22, you're like, there's a 50% chance you're in either one. And so that's what impurity is. This is a more impure node than this one down here. But nonetheless, I guess all of them were like that, and this was the best one to choose. I think that it wasn't good, and none of them were good, and it just chose it. Here's the thing. How do we measure the impurity of a node? We just talked about the fact of them being balanced like this is not good, and then being imbalanced between the classes like this is good because this is a more certain prediction of class than this one. Well, you measure impurity using the Gini coefficient. You'll see here you have Gini equal to 0.5 on the decision tree. If there's an actual like straight up balance, like half and half here, then we're going to have a Gini of 0.5. You see down here, as the balance between the classes grows, the Gini coefficient goes down to 0. And so that is a good thing. You want the Gini coefficient to be 0. You see down here in class, in the corner, 5 are in class 1, 0 is in class 0. Gini coefficient was 0. That means for sure, we have a good amount of certainty there on whether it's class 1 or class 0, and it's class 1 in that case. So that's the Gini coefficient. It measures impurity or the imbalance between those classes. And then what we're going to do is one way to reduce overfitting, because this model decision trees can overfit the data just like any other model, is that we're going to limit the height of the tree. Here we have a 1, 2, 3 height or depth tree. And if you can actually learn 100, a height of 100 if you wanted to, the only problem is that you'd get if your data set allows it, you can learn 100. The only problem is you run the risk of overfitting to the data. The deeper the tree, the more complex the decision-making process, the more likely you've overfit the data. So what I'm going to do is I'm going to hop into training a decision tree model, and then after that, we're going to talk about random forest, which is not just one tree, it's a collection of trees.